So the graphing sine and cosine functions. The graph of the sine and cosine functions are made by evaluating each function at the special angles on the unit circle. The input of the function is the angle in degrees or radians. We will be working just with radians. That's why radians is underlined. The output is the value of the function for that angle. We can unwrap these values from the unit circle and put them on a coordinate plane. And I have some examples in your notes as well as up here. So first we're just kind of learn how these graphs come about. What are these values? All right, so you can graph the function f of x equals sine x on the coordinate plane by using y values from the points on the unit circle where the independent variable x represents the angle theta in standard position. So x is the angle in radians and y is the value of sine for that particular angle. Right? And those all come from our special right triangles that we learned in the previous set of lessons. Right? So here we have sine. Right? So here we have some points on sine. Right? So 0, 0. Right? So sine uses the y value. So if my position is 0 on the right on the x-axis there, right? Sine is going to be 0. All right, here we have some more values. So here this red triangle, see the red triangle, was a pi third. So these are just some values. Pi thirds, right? So pi thirds, sine uses opposite and the hypotenuse. So square root of 3 and 2, right? Because pi thirds, we know that's our 1 square root of 3, 2 right triangle. All right, so pi thirds square root of 2. So there's a point, and so now if you look over here where the graph is, let's kind of tie them all together. So here is the position on the circle as we're going around and around the circle. All right, here is the point, pi thirds, 3 pi halves. There it is on the graph. See, I just kind of made it a little redder there. All right, so now we have another triangle. All right, so that other triangle, here we're at 5 pi 6 radians. So that means if we were to go all the way, that would be 5 pi 6. So the reference angle there is pi 6. Right? So pi 6, opposite that would be, same as 30 degrees, would be a 1. And then we don't care about the adjacent because sine doesn't use adjacent. It uses just opposite and hypotenuse. So the hypotenuse would be 2. Right? So the reference angle is pi 6. The actual principal angle is 5 pi 6. So 5 pi 6, 1/2 is the point, right? Because 5 pi 6 is the measure of that angle in radians. The trig ratio that goes with 5 pi 6 when we were evaluating is 1/2. So now we have the point 5 pi 6, 1/2 on the graph of sine there. Right, so now, I almost forgot to mention our quad angles. Our quad angles are wonderful angles because they're so easy to graph. Here is pi halves 1. Right, so at pi halves, sine is the y values. Right, 1 is that value. So right over here, black dot is getting a little darker. We have pi halves 1. Right, so that's that point there. If we continued around the circle, so we already did 5 pi 6, and we go to pi, 6 pi 6, or pi, right? Sine is 0 at pi, right? So pi 0 right there is a point on the graph of sine, an important one. It's an x-intercept. 0, 0 is an x-intercept. Pi 0 is an x-intercept. Right, so we continue along. We've got a point in the third quadrant there. Right, so that is 4 pi thirds. Right, that's the principal angle. Right, which the principal angle here goes to, that would be 4 pi thirds. Right, the reference angle is pi thirds, right, because we'd go back to the x-axis, and we know that opposite pi thirds, or opposite 60 degrees, is the square root of 3. That's going to be negative because we're below the x-axis. Right? And then the hypotenuse is 2. So 4 pi thirds, negative pi third halves is a point on the sine graph. Here's that point. Here we can see the triangle that comes from right here. Right? There it is on the unit circle. right? And here it is graphed, 4 pi thirds negative square root of 3 halves, right there. Right? And so these values, those y values, just come from our special right triangles. And then, of course, 3 pi halves, right? Sine's going to be -1 there. So here we have the point 3 pi halves, -1. That's a great point there. And then going into the fourth quadrant, right? So here we have the 11 pi 6 angle, right? So let's see if I can draw that in without messing up all the others. There we go, right there. All right, we know the reference angle for that would be pi 6. Right, so opposite pi 6 is 1, but we're below the x-axis, so it's -1. Hypotenuse is 2. So we have the point 11 pi 6, -1/2 on the graph of sine, and it's right over here. So very different, a little bit different looking graph, right? We don't have 1s and 2s, right? We're gonna purposely plot values that work with sine and cosine, which are in terms of radians, right? So feel free to number your, and so, just number your graph. It needs to be, each, on the x-axis, you need to be consistent what each line is, but you can just label it with pi halves and pi's and 3 pi halves and pi fourths. And so on the x-axis, our graphs are going to be radians, right? So for x here, this is in radian measures. X is radians, so you can write that on this graph. You have this graph in your notes. And our y value is just going to be the heights, right, of our function. Right? So y is not in radians at all. Y is just in integers or fractions or whatever it is, right? So y is not in radians, but x is in radians. I don't know what to call y. Y is just the heights, right, of our special right triangles. So not in radians, but important to note x is in radians, right? Actually, let's put y as trig values. That would be, y is the trig values. That's a better way to say that. All right, so here's some points. So now you can see that some points are easier to graph than others. Maybe square root of 3/2, maybe that's not so easy. We could get decimal equivalent, but maybe that's not as easy as, say, pi halves 1, right? Or pi 0, or 2 pi 0, right? So some points are a lot easier to graph than others, and we are going to take that into consideration and use those points that are easy to graph when we're trying to graph our sine and cosine functions. But I want you to know that every single point on that circle is represented on the graph. The ones that come from special right triangles that we could easily find the values for, and even the ones that don't and would be hard to find the values for. Right? But it's a smooth curve, and so we know once we've got a few key points, we know how to draw our graph. So similarly, the function f of x equals cosine x can be graphed on the coordinate plane by using the x values from points on the unit circle. Right? So the x is our angle measures in radians, and y is the trig values. Okay? And so actually, oh, you don't have this one in your notes. You have the next one in your notes. Right? But here's one of them. And you don't need to copy down. But write down the x's radian measures when you get to one that's in your notes. So this one's not in your notes. But I'm trying to help you see how this unit circle relates to our graph. Right? There's actually, I've seen a nice visual of that. Maybe I'll post that. So graphing and the visual is animated. So graphing the trig functions here. So we see in figure 5.1.1 over there on the side that any point on the unit circle has coordinates x, y. So our x values on our coordinate on our graph are radian measures, but on the unit circle, right, the x represents cosine and the y represents sine, right? Because the x values don't represent radian measures, right? The amount of turn is the radian measures, right? So 0 here, so pi, that's that's in radians, right? But this point here that I marked as pi 0, right, on my circle would be also be negative 1, 0. So this over here. So this right here is the point negative 1, 0 if I'm graphing the circle. When we're taking the values from the circle and putting them on the graph, right, pi looks at how much we've turned, all right, not our location on a coordinate plane, right? The location on a coordinate plane would be at negative 1, 0, right? But in terms of how far we've turned, it's pi degrees, right? So when we're graphing our trig functions on our coordinate plane, we're looking at the x being the radian measures and the y being the values of the function. When we have the graph of a unit circle, x is cosine, y is sine. Because cosine uses x and sine uses y. Okay? All right, so if we were to take the y values and the angle measure, we're going to get the graph of sine. If we take the angle measures for x and the x values on the circle, we're going to have the graph of cosine. All right, so here it just kind of shows you that at pi 6 here, and here's pi 6 over here, so this ends up being 1/2. Right? So this was still sine. This is the point pi 6 1/2. Right? And so as we move along here, pi thirds, right? This is the point. So now this is pi thirds. Right? And this reference triangle here, this is the square root of 3. So that's going to be square root of 3 over 2. Right? And then pi halves going right along here, that's the point. So in the pi halves is the angle measure. We use the y value for sine, so that's the point pi halves 1. And this one crowded up. This one took up so much space, we can't point out pi half 1, which is right there. All right, so that's if we were to unwrap all those triangles and graph those triangles, we would have our sine ratio, or sine graph. I think I put this one in your notes. So there it all is. All right, so unit circle definition of the sine function. All right, so the x's are measured in radians when we're graphing our sine function or a cosine function. And then the y values are the heights of our functions. Let's write the heights in because we know a lot of them. All right, so pi 6 here, that's going to be the point pi 6, and that is 1/2. Over here at pi thirds would be the point pi thirds, boy, it looks kind of lousy, square root of 3 over 2. At pi halves, my writing's too big. At pi halves is the point pi halves 1. At, that works out better with put an arrow there, at 2 pi thirds, which is right here. All right, so 2 pi thirds, and now we're coming over here. All right, so it's still going to be, opposite a third. So this is going to be, and we're still going to be positive. This is still going to be, this will be 2 pi thirds, and this will still be the square root of 3 over 2. 5 pi 6, that's this one over here. All right, so now we're opposite of 6, which is a 30-degree angle. So this one here is going to be 5 pi 6, and this would be, we're still above the x-axis, 1/2. Now we're getting below the x-axis. So pi here is at, this is pi 0. 5 pi fourths right here is that's going to be the point 5 pi fourths. And now we're over here All right, so that's our 45, 45, 90 triangle. So this is 1, but it's negative, and this is the square root of 2. So this is going to be negative square root of 2 over 2. Now I'm going over these values really quickly because I'm not teaching you the values. I'm just having you get a sense of where the values come from, because we learned how to do the values in previous lessons. 3 pi halves, now I'm right over here, right? And so this is the point, this would be the point 0, negative 1. So on the circle, for our graph, the angle measure is 3 pi halves, and the sine value is negative 1. At 7 pi fourths, now I'm over here, right? So y is negative, so that's going to be negative 1, and this is going to be the square root of 2. So this point right here is 7 pi fourths, and that would be negative square root of 2 over 2. And then we get back to the beginning again, which is this point back here. We've gone all the way around the circle. 2 pi 0. All right, so that's where the values come from. We're going to graph some very key values, and we'll learn about that. This whole lesson right now is just learning the parts, getting a sense of where that graph comes from. Right? That's all. How it comes from the sine values as we go along the unit circle. That's all that is. It's like we're peeling it apart, and we're stretching it out into the curve. That's how it is. And cosine's the very same way, except the values are different. So the graph of f of x equals sine. Domain is all real numbers. This will repeat forever and ever and ever and ever and ever and ever. And I'm on the second page, by the way, in your notes. Negative. And I have this in your notes somewhere. I have this listed, and I think it's at the bottom of the second page. The domain's all real numbers. Range negative 1 to 1. Brackets, endpoints are included. It does go through the points negative 1 and 1. We use parentheses because we're between negative infinity and infinity. All right, so here are some key values for our sine graph. And notice I did not graph every point, but I graphed the key ones. Notice where those key ones are located. Look at those y values. Why would I choose those numbers? 0, 1, negative 1, 0, because they're easy to graph. You can continue the graph of sine to the right and to the left. Right? We typically graph 1 period or 2 periods. We're going to be graphing 1 period. Right? Sometimes you'll be asked to graph 2 periods, generally not more than that. Graph of f of x equals cosine x. Domain is still all real numbers. It will just continue on and on and on forever and ever and ever on the x-axis. However, it's never going to get past negative 1 and 1. It just oscillate between those two values, just like sine. Right? Those values come from our unit circle, that radius of 1. Right? So that's why our sine and cosine are stuck between negative 1 and 1, right? And so there are some points there, some key points that are graphed, 0, 1, right? So remember that cosine uses the x values for the circle. That's its y values. Pi halves 0, so pi halves cosine is 0. Pi negative 1, back over on the other side, the x-axis, 3 pi halves 0 is cosine is 0 at 3 pi halves, and at 2 pi, cosine is back to 1 again. So this is the graph of cosine, and it repeats forever and ever and ever. Just like that, forever and ever and ever. You might notice that sine and cosine look a little bit alike. All right? The red graph is sine, and the blue graph is cosine. Look at that. They are actually just shifts of one another. Right? So cosine theta is if you just add pi halves to cosine theta, you got sine theta. Isn't that interesting? Right? Because it's using the same values, right? But they're different trig ratios for cosine and sine. But their graphs are very, very similar. Right? And so this is what it looks like when you can continue them. We'll just be graphing 1 period of them, so they won't look exactly the same. But the red is sine x and the blue is y equals cosine x. So basic sine and cosine curves. The black portion of the graph represents 1 period of the function. It's called 1 cycle of the sine curve. Right? Notice that it goes So once it repeats itself again, right? So goes from, starts at 0, goes up to 1, comes back to 0, then goes down to -1. Once it comes back to 0 again, right, that's the end of the period, right? So notice that its period is 2 pi. Takes 2 pi to repeat itself. Takes 2 pi for cosine to repeat itself. Cosine starts at 1. At pi halves, it's at 0. At pi, it's at -1. At 3 pi halves, it's at 0. And then at 2 pi, it's back to 1 again. So both sine and cosine have a period of 2 pi, unless we change the equation. So the black portion of the graph represents one period of the function for both sine and cosine. It's one cycle of the sine, and then we have one cycle of the cosine. Domain is all real numbers. That does continue on the x-axis. Though those measures in radians, those are just numbers. They just had to be in terms of pi, because pi would be better to graph, right? We could make them 1, 2, and 3, but then we're struggling to figure out where does pi halves fit between 1 and 2 and 3. So it'd be a lot easier if we just label our x-axis in terms of radians, and then we have nice pretty numbers to graph. So each function has a period of 2 pi. A few key points, and this is in your notes. So the key points in one period of the graph are the intercepts, maximum points and minimum points, right? And those are the ones we're going to graph, right? So here are some more values on the graphs of y equals sine x and cosine x. Do they look familiar? Hopefully they all do. They all come from our special right triangles, right? So the only one that's not represented here are the pi fourths. So anything that's a multiple of pi 6, pi thirds, and pi fourths is an angle from a special right triangle. We can calculate that out exactly. And even though we can calculate it out exactly, it's not so easy to graph. I don't know about you, I can graph 1/2 just fine, but then we get to square root of 3 over 2. I can get a decimal equivalent, but maybe not as pretty as some of the other values. However, 1s and 0s, those are pretty easy to graph. And those are the ones we're going to stick with, especially as we transform our graphs. We're going to stick with our maximums, our x-intercepts, and our minimums. That's going to be our 5 key points. All right, so for sine has 3 x-intercepts, a max and a min. That's its key points. And cosine has 2 x-intercepts, 2 maximums, and 2 mins, and see where they're located. So for sine, x-intercept at 0, 0, pi 0, 2 pi 0, and a maximum at pi halves 1, a minimum at 3 pi halves -1. Notice that every fourth of the way, which is very, very key, something important happens, right? So we start off at 0, 0. At quarter period, 1/4 of the way, we have a maximum. Halfway, 1 more fourth, we have an x-intercept. 1 more fourth, we have a minimum. 1 more fourth, we're back to an x-intercept. Cosine, right? So has 2 x-intercepts, pi halves and 0, 3 pi halves and 0. 2 maximums, 0, 1, and 2 pi 1, and 1 minimum, pi -1. So this is one period of each, which is what we'll be graphing. Notice that every fourth of the way, something important happens. So we start off with a maximum. 1/4 of the way, we have an x-intercept. 2nd fourth of the way, we have a minimum. 3rd fourth, we have an x-intercept. And then when we finish the period, we have a maximum. So graph of the sine function. To sketch the graph of y equals sine x, we're going to locate the key points. They are our maximum and minimum values. 0, 0, pi halves 1, pi 0, 3 pi halves -1, and 2 pi 0. And then we'll connect the points on the graph with a smooth curve that extends in both directions beyond the 5 points. Put a little arrow, right? And that will, because we're going to be graphing just one period. The graph of the cosine function. To sketch the graph of the cosine, we're going to locate its key points. Its key points are at 0, 1, pi halves 0, pi -1, 3 pi halves 0, and 2 pi 1. And again, just draw an arrow at the end of it because the graph isn't ending. It's just we're only graphing one cycle, and we know it's going to repeat and do the same thing over and over and over and over again. So we'll just graph one cycle of it, one period. Right? I'll leave this one in this lesson. So here, because this is at the bottom of your notes, it's the properties of sine and cosine. They are very similar in a lot of ways. Their domain is a set of all real numbers, or you can write that as the symbol, or negative infinity to infinity. Their range is from -1 to 1, or you can write it as it is there in interval notation, or set notation, excuse me. The maximum value is 1, minimum value is -1. The graph is a smooth curve. Each function cycles through all the values of the range over an x interval of 2 pi, and the cycle repeats itself indefinitely in both directions on the x-axis. So we're going to look at some key things, because we're not just going to keep graphing y equals sine x and y equals cosine x. That'd be boring. I just showed you that. We're going to add some things to our graphs. Maybe they'll go through their cycle faster. Maybe we'll make them go up more than 1 and -1. Maybe we'll move them around. All right, so let's see what we can do to sine and cosine. See you in the next lesson. Bye for now.